Let's take a look at probability rules. Now, probability deals with experiments that yield random short-term results or outcomes yet reveal long-term predictability. The long-term proportion which a certain outcome is observed is the probability of that outcome. Probability is how likely it is that some event will happen. We're looking at, we start studying children born in a particular town. And there it goes. Wasn't writing. So initially, there's 5 children. 4 of them are boys. I keep studying it. There's 10, and then there's 6 boys. Go to 20, and all of a sudden there's 9 boys. And 100, and maybe it goes to 49 boys. So they deal with a long-term proportion, which a certain outcome observed is the probability of the outcome. So probability that it's going to be a boy is 49 over 100, or 49%, 0.49. Probability is how likely it is some event will happen. So if I study enough of these, maybe I get up to 10,000. And maybe I find 4,999 are boys. Then you can be pretty sure that there's 1 in 2 chance that a child being born will be a boy. That's what it's referring to. Now, the law of larger numbers. As the number of repetitions of a probability experiment increases, the proportion with which a certain outcome is observed gets closer to the probability of the outcome. What does that mean? Well, and at first I only looked at five children, and 4 of them were boys. It would appear that there's a large number of boys that are born here. But if I study enough of them, law of large numbers, then this will actually go to what the true value is. We know it's 1/2. Probability you're going to get a boy or girl when a child's born is 1 out of 2. 50%. Now, we got something called a sample space. This is for a probability experiment. Sample space is a collection of all possible outcomes. Do you know this? Way back when. This was back in probably 1995. I was trying to put a hard drive in my computer, and I'm not very good hardware-wise. But I had 2 hard drives, and they got these little pins sticking out the back, like this. And you connect these together with the wire, and that was the easy part. And then you're supposed to put a little plastic piece over 2 of the pins. So I might put it over those 2, and I might put it over these 2. And by having the proper I don't know what that is. It makes a circuit, I think, completes a circuit. By having those on the appropriate place, you can have a primary and secondary hard drive. You can have 2 hard drives. Well, I was up at it. This was before I had air conditioning in my house. I'm sitting here in the middle of the night trying to get this to work. At one point, nothing worked. I had no hard drives. I had nothing, and I finally gave up. About 2 a.m. I said, "Oh, this is ridiculous." I went to bed. Woke up the next day and went to tackle it again. And what I did is I labeled these. So we had gave them some kind of letter, like this is A, this is B, and this is C, and this is D, and this is E, and this is F. And I listed all the possibilities. Well, I could have A and D. So I have the little plastic piece over this, little plastic piece over this. I could have A and E. A little plastic piece over this, little one over this. I could have A and F. I could have B and D, B and E, B and F. I could have C and D, C and E, and C and F. This would be my sample space. Actually, once I did that and I tried all the possibilities, there really wasn't that many. I was up and running no time flat. If I had thought of it the night before, listing down all the possibilities, then I would have saved me some headaches. But this is our sample space, all our possible outcomes. Now you could be looking at a problem dealing with children. You're looking at children being born, whether it's a boy or a girl. And you got 3 children. Well, our sample space, you could have first child's a boy, second child is a boy, third child's a boy. First child's a boy, second one is a boy, third one's a girl. Boy, girl, boy. Boy, girl, girl. Girl, girl, girl. Girl, girl, boy. Girl, boy, girl. And girl, boy, boy. These are all of our possibilities. So that's our sample space. And just in case you look at this later and wondering what in the world is this referring to, these are our sample space examples. Now, event, any collection of outcomes from a probability experiment, denoted with E. Doesn't have to be E, but... Now let's actually take a look at an example. It says, list the sample space of the following. You're picking 2 people from the following group. Order doesn't matter, and you cannot pick the same person twice. Order doesn't matter, and you cannot pick the same person twice. So I got Bill, Sally, Mary, and David. And we're picking 2 people. So I got Bill and Sally. I got Bill and Mary. And I got Bill and David. So I pick my first one and then I pair it up with each of these. Well, I can start with my Sally. Sally and Mary. Sally and David. Now I wouldn't want to put Sally with Bill again because that we already had that down here. Then I'll go to Mary. And the only one that can be paired up with is David. And David is here at the end, so there's no pairing. So these are our possible sample spaces. Now you have to read carefully when it says. He says you cannot pick the same person twice. If that wasn't in there, well then we could have Bill and Bill, Mary and Mary, and so forth. Cannot pick the same person twice. And order doesn't matter. So those 2 right there kind of help dictate how the problem's going to go. Now P is for probability, and you can label specific events with letters like A, B, C, and E. Probability of E, that's what that notation looks like there. That says a probability event E occurring. It's kind of like function notation in algebra. Now, the rules of probability, all probabilities have to be between 0 and 1, including 0 and 1. Can't have any negative probabilities, can't have any probabilities greater than 1. You can think of this as percentages. So like 0 is 0%, 1 is 100%. If I told you there's a 200% chance it's going to rain today, it doesn't make any sense. Because 100% means it's for sure, it's going to happen. So why say 200 when 100 is the highest you can go? And 2, the sum of all probabilities of all outcomes must equal to 1. Can't have it equal to some other weird number. Like if I told you probability it's going to be sunny today is 80%. Probability it's going to be rainy is 60%, and snowy will be 20%. Well, this doesn't make any sense. This adds up to 160%. That's what that's saying. It should add up to 100%. Now we have something called a probability model. This lists the possible outcomes of a probability experiment and each outcome's probability. And this kind of sums up what we just talked about. All the probabilities have to be between 0 and 1, and they all have to add up to 1. So let's look at our first example here. It says determine the following as a probability model. If I look at all the probabilities, they're all between 0 and 1. There's no negative probabilities. There's no probabilities greater than 1. So that's good. Well, now they have to add up to 1. Well, 0.2 plus 0.1 is 0.3, plus another 0.3 is 0.6, plus another 3 is 0.9, plus 0.1 is 1. So they add up to 100% or 1. So the answer here is yes, it is a probability model. Now for 3. Same question. Is this a probability model? Well, if you look at this, Bill's negative 0.3, Sally's 0.5, Henry is 0.8. These together add up to 1, but this is a negative probability. Do they add up to 1? Yeah, they do. Okay. This is a negative probability, which we can't have. So the answer here is no. There is a negative probability. I think the next one is to construct a probability model. So let's take a look at how to do this. I'm going to save this and start a new page. I think this is probability rules, page 01.pdf. There we go. This is how many times you break the law in a week, and I use this for example for students. Say 0 to 100. How many times they break the law in a week? There's 2 of them that will fall in that range. Between 101 and 200 is 10. Between 201 and 400 is 15, and over 400 is 25. Now I always look at people. I show this example in class, give this example, and people look at me funny. It's like, I don't break the law 400 times a week. Well, if you think about it, if you drive the speed limit, well, that gauge could be going over the speed limit by just a little bit. And if you go over the speed limit, you're breaking the law, period. And if you go back under the speed limit and then back over it, you just broke the law at a separate incident. Those who have ever got a speeding ticket, they'll tell you that you don't get a free pass for the rest of the day. You get pulled over again, you get another speeding ticket. So when you think about somebody driving, this is actually probably a pretty low number. If you jaywalk, if you're not exactly in the crosswalk when you cross the street, you're a foot on this side of the crosswalk. That's jaywalking, so you're breaking the law. So this is actually probably pretty low compared to that, but we'll go with this. So this is my number of laws broke. And this is our frequency. So I got 0 to 100, 101 to 200, 201 to 400. By the way, you do have to wonder what's the sanity behind having laws in place that the average citizen breaks 400 to 500 times per week. No way you can enforce that. If you did, the person would be bankrupt and people go bankrupt every week. What we're going to do to get a probability model is we're first going to add the frequencies together. And I'm going to get my calculator handy here so I don't screw up something. I should add up to 52, but let me double check myself. 2 plus 10 plus 15 plus 25. 52. Okay, so for our probability then, we're going to take each frequency, divide by our total. So we'll take 2 divided by 52, 10 divided by 52, 15 divided by 52, and 25 divided by 52. Let's see, 2 divided by 52. Excuse me. And I'll take this to 3 decimal places. There's no consistency. It's the standards, aren't in place. It tells you how many decimal places. Probably kind of whatever you feel like. 0.192. 15 divided by 52. 0.288. And 25 divided by 52. 0.481. Now, it is very possible that these do not add up to 1 because of my rounding. 8 plus 2 is 10, plus that is 18, plus 1 is 19, which means this isn't adding up perfect. So what I can do is I can come over here, take that 1, and make it a 2. Doesn't matter. If I tell you there's a 48.1% chance or 48.2% chance, that's basically 48%, isn't it? Now, I say this because if you give this to somebody in a business meeting, somebody will be bored and they'll be sitting there adding these together, and it's like, oh, where's the missing 0.1% at? So fudge your numbers and make sure they add up to 1. And that'd be our probability model. Now, probability is decimals. We're used to thinking in percentages. Some people will put these in percentages. What this says is if I pick out somebody at random on campus, the probability that they have broke between 201 and 400 laws in a week is going to be 28.8%. Doesn't quite fit like that, but you can think of it in those terms. Okay, what does probability mean? If you got 0, that's an impossible event. A certain event is 1. 1 is 100%. And any event is between and including 0 and 1. 0.5 means 50-50 chance. Now, unusual event is an event that has a low probability of occurring. And our guideline is a 5% cutoff point. So if you come up with probability of 0.03, that's considered unusual. If you come up with a probability of 0.82, that's usual. Again, 5% is our cutoff, the 0.05. So use that on any problems asking about an unusual or usual event. Now we got our empirical approach, and this is real life. This is where maybe I want to study how many boys are born. What's the probability of getting a boy in Ark City, Kansas? Well, if I break into the hospital at night and go through birth records, I can count how many there were. And maybe I find that there was, out of 5,000 births, 2,550 of them were boys. And that'll give me my probability. Well, there's a problem with this. First off, I'll go to jail, so that's not good. Has a very high price. Maybe you spend 10 years behind the bars. Have felony, never go work again, or a decent job. So this right here is sometimes not the best thing to get, but it does give us a probability because this is actually what happened. So then you can use that to gauge what's going to happen in the future. Take a look at an example of that. Says a survey of 700 randomly selected students showed that 100 of them believe in ghosts. What is the probability a randomly selected student believes in ghosts? Well, we use the empirical approach here. The total goes on the bottom, so we put 700 here, and 100 of them believe in ghosts. We put 100 up on top. Your large number is always down below. It's 100 divided by 700. And I don't know why I don't got both lights on my room. Let me turn that on so I can actually see. There it is. Okay. So I got 0.1429. So approximately. So it'll be 14.29%. So if I randomly pick somebody out at random, that's a chance they're going to believe in ghosts. Now we have a classical method. This was real life. Our classical method says we look at how many possibilities are there. This is theory. Well, for a particular child that's born, it can either be a boy or girl. So there's 2 possibilities. Of those possibilities, one of them is a boy, so I'll put 1 up here. So that gives us 1/2. Now this right here, decimal-wise, is 0.5. And this one is equal to 0.51. Now the theory side, what you'll find is it will be the same as real life. If I had taken enough in real life, if I take enough, a look at enough birth records, I'll see it will be the same as the theory. Now the benefits, real life, this cost me a week's worth of time maybe. I broke in the hospital every night, and I ended up in jail at the end. This theory side, that took me 5 seconds, and I came up with the same results. And this is a classical method. The theory side is the number of ways E can occur over the number of simple or different simple events. Let's take a look at some examples of that. It says a box contains 5 blue markers, 3 red and 7 green and 10 black. So 5 blue, 3 red, 7 green, and 10 black. I used to do this with balls, like green balls, red balls, and so forth. And then I said something inappropriate one semester, not on purpose, but I don't use those anymore. I'm gonna use markers. Okay, now it says what is probably a randomly selected marker is black. So we're picking one out, and we're looking at the probability it's black. Well, I have to see how many I have total. There's, see, 7 plus 3 is 10, 20, 25 total. So put 25 down below. Then I count how many are black. Well, there's 10 black markers. So we get that. And that'll give us 0.4 or 0.40. So 40% chance. B, what is probably a random selected marker is blue. Well, there's 25 total, and of those 25, 5 of them are blue. So we got 5 out of 25. Which gives us 0.2. So 20% chance. So those would be your answers. Let's take a look at another example. It says excluding leap year and the probability of being born on any particular day is the same as any other day. A, what is the probability a random selected person is born on the first of the month? First of the month. Well, there's 365 days total, and there's 12 firsts of the month. There's January 1st, February 1st, March 1st, so forth. So this would give us our probability. That's 0.0329. By the way, look at this. Is this an unusual event or a usual event? It's less than 5%, isn't it? So this would be considered unusual. B. What is probably a random select person is born in January? Well, there's 365 days, and there's 31 in January. And that gives us 0.0849. Is their probability. C. What is probably a random select person is born on the 31st day of a month? 31st day of a month. Let's see. 1, 2, 3, 4, 5, 6, 7. So it'll be 7 out of 365. And that gives us 0.0192. Now this first one, select the person who's born on the first of the month. Actually, the second one. Was probably random was born in January. Some people say 1 out of 12 here, which is close, but it's not correct because the months have different number of days in them. So you can't say 1 out of 12. Excuse me. Let's take a look at this one. It says, out of a standard deck of cards, a card is drawn at random. And that's kind of true throughout this entire class. Everything's random. If it isn't random, then there's no probability there because you're skewing it. You're making sure it's going to happen. I guess I shouldn't say there's no probability, but there's no use for us to calculate the probability. Now, first one says find a probability it's a heart. Well, there's 52 cards, and of that, there's 13 hearts. This is 0.25. Sometimes they'll leave the fraction or leave the answer in fraction form. Sometimes they'll put it in decimal. Find a probability it's a king. Well, there's 52 cards, and of those 52, 4 of them are kings. And we get 0.0769. And then C, find a probability it's a red card. Well, still 52 cards, and 26 of them are red, which should give us 0.5 as our probability. Let me save this. And let's look at our next topic. This is simulation method. And its formula is probability of E is the frequency of E over number of trials of experiment. Let's look at Excel to understand this simulation. Okay, we're going to look at simulating having 3 children. So here's child 1, child 2, child 3. I'm going to do an equals, rand between, and then beginning parentheses, and then 0, comma 1. What this is going to do, and it has to match that exactly what you're seeing there. You have to have the equals, has to be rand between exactly as you see it typed, beginning parentheses, 0, comma 1, and closing parentheses. This will give us a random number between 0 and 1. Now press enter on that. Now what we're looking at here is a girl is going to equal to 1, and a boy is going to equal to 0. So here, the first child born is a boy. Now I'm going to click this cell and move my cursor down to the lower right hand corner until it becomes a plus, and I'm going to click my left mouse button and hold down and drag to the right. I get that. Then I'm going to come down here in the lower right hand corner of C2, and I'll click and drag down. And like to 40 or something like that. So that's what we mean by simulating. Well, let's take a look at the example we have, which is based upon this. It says, simulate rolling a die 100 times and find probably getting either a 5 or a 6. Okay. So we're rolling a die 100 times, find probably getting a 5 or 6. So this is roll the die, and we're going to say equals rand between, and it'll be 1 to 6. Again, it has to be exactly like you see here. Equals rand between beginning parentheses 1 comma 6 closing parentheses, enter. And we're saying we're rolling it 100 times. So I'm in A2. I want to go down to A101. I don't want to be A100 because my title took up the first cell. So again, I'm clicking this cell, and I'm putting my cursor in the lower right-hand corner so it becomes a plus, and I'm going to drag it down to 102. There we go. And we've simulated rolling a die 100 times. Now look at probably getting a 5 or a 6. So what I want to do is I want to count how many 5s there are. you're going to see that anytime I make a change, it redoes the numbers. And that's fine. It's just a simulation anyway. Now here I'm going to do an equals. And I'm going to type count if, beginning parentheses, and I do my range. So I said A2 colon A102, comma 5. And then close parentheses. Again, it has to be exactly like this. Equals, count if, beginning parentheses, your range of date, where your date is at, comma, and then the value you're looking for, and then closing parentheses. What this is going to do is it's going to go through and through the range A2 through 802. It's going to count how many 5s there are. Press enter. There's 20 of them. Here I'm going to do the same thing. I'm going to do a if count if A2 colon A102, comma 6. This is going to go through and count how many 6s there are. And again, it has to be typed in exactly as you see it here. Now press enter. And we get this. Now total, I want to sum these up. So I'm going to come up in my home tab, click the auto sum, and click the little check mark here. So that means we got 39. So for our probability of 5 or 6, then we're going to do an equals this value right here divided by 100, since we got 100 of them. Now this one's kind of boring because if you divide by 100, it's just this divided, move 2 decimal places. So we got 38% chance it'll be a 5 or 6, which makes sense because there's 6 faces on a die, and 2 of them are 5 or 6. That's like 2 out of 6, 1/3. It should be about that. So that's simulating a roll of a die. Now our fourth method here, I never really put this on a test. This is subjective probabilities. This is guessing or estimating. This is what we do a lot of, unfortunately. Example of that. What is the probability of seeing a motorcycle rider who is a woman? And probably no need to say this page, but what's that probability? 30%? 60%? It's subjective based upon your own experience. Maybe the 30% that think that they just came from the Baptist church and that's where they hang out. And there's not a whole lot of bikers that are in the Baptist church. Not saying it's good or bad. There's 60%. Maybe this is the person who hangs out in biker bars. He knows how many women ride by motorcycles. So is either of these correct? Is either of these wrong? We don't know the true answer. Both of these are correct because they're based upon their own experience, what they've seen. So the reason why subjective probabilities will never be on a test is there is no wrong answer. Whatever you put down is right because it's based upon your own experience. Now I say guessing, it's an educated guess. You're usually just not making numbers up, but you're doing it based upon past experience. The last thing I want to talk about is the rounding off probability. This book doesn't do this, but I like to talk about it. Sometimes the current textbook will put it into fraction form, sometimes decimal, and that's what a lot of the books do. Now this says for our rounding it off, we got an exact fraction, exact decimal, or round off to 3 significant digits. I want to mention something about the significant digits because it's important. If I told you this was a probability you're going to win the lottery, and the lottery is 150 million. Well, you'd swarm out there, you'd buy a bunch of lottery tickets, wouldn't you? It's like, well, there's a chance I'm going to win, chance I'm going to be in Hawaii. If I rounded this to 3 decimal places, then the probability you're going to win is 0%. It's like, why would you play then? If you know you're not going to win, why would you play? But if I rounded to 3 significant digits means you ignore these leading zeros. The 3 significant digits would be that right there. And if this had been like a 3, I would have, if this was 5 or greater, we'd round up. Otherwise, we round down. So it gets this. This is why significant digits are better. Rounding to 3 decimal places may look like there's 0 chance. Rounding to 3 significant digits, you can see that there is a chance. And that's the end of that section. So Let me stop both recorders.